All right, guys. Let's just start with questions about the homework because I think a lot of people have questions. That's not it. So today's homework is this. Did anybody have any problems with A, B, C, D? I know a lot of people had problems with C. Has anybody not seen what I said in the group and need me to go over how to solve this one? Okay, yeah. What's up? D? Anybody else have problems with D? Okay, so a couple people. Basically, D is one loop, right? It's just one single loop, okay? And there's 1 milliamp flowing through the loop, okay? That means that right off the bat, you can find the voltage drops across all these resistors, okay? There's 1 milliamp flowing through this 2K, so here, you know what, I'll do it real quick just because it's really quick. Let me just draw it out. So this is homework 7, 1D. Current source, resistor, ground, resistor. So this is pretty similar to the quiz I gave that everybody struggled with, where it was just one loop and a current source. So I want to go over this so that if you thought that this was difficult, I don't want you to think it's difficult anymore after today. And 1K. Okay, so this is one loop, right? Which means that 1 milliamp flows through the entire loop. So the current through this entire loop, that's just 1 milliamp. Okay? So that means through these resistors, right? I've got 1 milliamp flowing there. Oh, sorry guys. Thank you for letting me know. Nice. Alright, so I've got 1 milliamp flowing through this entire circuit, right? I've got 1 milliamp flowing here, obviously there, and there. So using Ohm's law, I can find the voltage drops across all of these resistors, right? Voltage, you know, it goes plus to minus because the current's flowing in this direction. And there. And now 1 milliamp times 1K gives me 1 volt, right? Then here, 1 milliamp times 1K times 2K gives me 2 volts. This one gives me 1 volt, 2 volts, and 1 volt. Those are the voltage drops across all the resistors. Is that clear? I don't know any of the voltages yet. I just know the drops across the resistors.
Based on what I got at the top, those 1 volt and 1 volt, I thought it would be 0.
So this voltage is 0. That voltage is 0 because that's ground. Is that what you're talking about?
Yeah.
That's right. That is 0 volts. So what I know is I know the drops across all the resistors, but I don't know this node voltage. I don't know this node voltage. This node voltage. I don't know any of these voltages yet. That's what we're gonna find now. Okay. So basically, if I'm at 0, right? I know this is 0. That's my starting point. If I didn't know that was 0, I couldn't go anywhere from here. But I do know that that's 0. And this is telling me that I'm going to go down by 1 volt, right? So this is negative 1 volts. Okay? This is negative 1 volts, and this is telling me that I'm going to go down 2 more volts. So this is negative 3 volts. Does that make sense? So I just go around just like this. This is telling me I'm going to go down another volt, right? And then again, right? And so if I want to come back over here, this is telling me that I'm going up a volt to get to 0. I'm going down a volt to get to 0. So this should be 1 volt, right? And then this is telling me that I dropped 2 volts across this 2K. So that means that this voltage right here would be 3 volts. Because I went 3 volts, I dropped 2 and I got to 1, then I dropped 1 and I got to 0. So those are all my voltages. Does that make sense?
Yeah,
Does that make sense? Any questions about anything there?
Yeah, how can the ground be in the mid-volt for sure?
Ground could be anywhere. All ground is a reference. It's a 0-volt reference. If I don't have this ground here, we don't know anything about any of these voltages. We know the drops, but we don't know any of the voltages. So I could throw ground anywhere, and that's your starting point. If I threw ground down here, all these voltages would be drastically different. The whole thing would shift, right? So wherever I put ground, that's just my starting reference point. I can reference that as 0, and I go, okay, I drop 1 volt there, I drop 1 volt there. You can start to find the voltages throughout the circuit with reference to ground. If you don't have ground, we don't know those voltages. Okay? All right. Any questions about that? Any other questions with the homework? I heard somebody say something.
Does that circuit follow KVL?
This?
Yeah.
Yeah, well, it would follow KVL, but you...
Oh, we don't know the voltage of the current source.
Right,
So
so
that's where I was freaking out. I was like, wait a second, this is not add up. But then-
So if I put a voltage source here instead
Yeah.
of a current source, you'd
Yeah,
use KVL.
Absolutely.
Yeah?
Yeah.
On 2B, was it? So, yeah, so on 2B, I was having a hard time figuring out what exactly to do.
Okay.
Because there's a current source that's in the voltage source.
So I'm going to go back over Thevenin and Norton today. Would everybody be cool if I just solved both of these?
Yeah.
All right. So let's do that. Because I know Thevenin and Norton are a lot. There's a lot going on. So I'm going to go back over today, hopefully clarify some things. And then hopefully you feel a little bit more comfortable. There's more Thevenin and Norton on the next homework because I want everyone to get familiar with it. But let me start with homework 7. And what is this? 2A? All right, so this one I'll solve first. So I'm going to do this as if I were solving this for a homework. Like if I were in this class and I was doing this homework. So this is 1K, 6K, 3K, 5 volts, and ground. And then my load is the 1K. Okay. So I asked you guys to find Thevenin and Norton equivalent circuit with the load resistor removed, blah, 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 blah. So what I'm going to do is I'm going to split the page into Thevenin and Norton. So this side will be my Thevenin. I'll do different colors too. This side I'll do Thevenin. And this side I will do Norton. Okay? So the first thing you need to do is you need to solve for V out in the original circuit. This is just what we've been doing this entire time, right? We're not going to do anything crazy. There's no Thevenin and Norton involved yet. You're just finding V out A because that's what we need in order to reference later and see if we did our Thevenin and our Norton correctly. We need to know what V out A is, okay? So if I'm going to solve this circuit, what I would do is I would combine the 6K and the 1K in parallel, and then I have just a voltage divider, right? So 6K in parallel 1K, I'll just do it real quick. That's 6 over 7. Whoops, 6 over 7 gives me 0.857K. Is that right? Does that sound right to everybody? So my original circuit then would turn into 3K, and then that equivalent, whatever the heck I just said, 0.857K. And this is 3K, and this is 5 volts. So if I go ahead and make a voltage divider here, I can find my V out A, and that's going to be 5 times 0.857K, basically over 3.857K. Everyone agree with that? Voltage divider. So whatever that is divided by 3,000. Whoops, so 857 over 3,857 times 5. 1.111 volts. I think that's right? That's what we got in SPICE. So my V out A is 1.11 volts. I've done nothing new so far. That's just finding V out, exactly like we would in any other circuit, right? Everybody good so far? Okay, so now what I'm going to do is I'm going to Thevenize the circuit. And when I Thevenize the circuit, what I'm trying to do is I'm trying to replace the circuitry with a voltage source in series with a resistor. That's Thevenin's theorem. It says that we can replace any linear circuit with a voltage source in series with the resistor. So let me just draw my model Thevenin circuit. It looks just like this. This is my R Thevenin, and this is my V Thevenin. Okay? So I need to find R Thevenin, I need to find V Thevenin. And what I ask you guys to do is to find the Thevenin and Norton equivalents for the given circuits when the load resistor is removed. So it should be noted that you don't have to find Thevenin equivalents with the load resistor removed. You could find a Thevenin equivalent for the circuit with the load resistor in there, but it makes it easier when you remove the load resistor. So that's why I'm telling you to do that. So what we're going to do first is we're going to draw the original circuit again, and we're going to remove the load resistor. 6K, 3K, 5 volts, and then over here I would have had a resistor, but I removed it, right? I removed my load. My 1K was my load. And this is the voltage that I find, right, across the load terminals. That is my Thevenin voltage. So that's the reason why we're doing this. Is all we're trying to do now is we're trying to find the Thevenin voltage. This is just another voltage divider, right? So V Thevenin is 5 volts times 6K over 9K, or basically 2/3 of 5, which I think is what, 3.333. All right, let me try it. 5 times 2 over 3, 3.333. So V Thevenin is 3.33 volts. Okay? So now I have my Thevenin voltage. That's 3.33 volts. Right? Now I need to find R Thevenin. And then I'm done with the Thevenin circuit. I'm done with the Thevenin circuit if I find R Thevenin. In order to find R Thevenin, I'm going to draw this exact same circuit, except I'm going to short my battery. I'm going to short out batteries and open up current sources. In this case, I have a battery. I'm going to short it. And now I'm going to measure the current, or the resistance, between those 2 points. And that can be complicated. It sounds complicated, but I gave this analogy last time. What I'm doing is I'm basically sending a current in through this node, and I want to see how much resistance does it have to go through in order to get to this node. Okay? And in this case, it has to go through a 3K and a 6K in parallel. Everybody see that the 3K and the 6K are in parallel? Okay, so my R Thevenin basically is that equivalent resistance. It's going to be 6K in parallel with 3K, which is equal to 2K. Great. So that's my R Thevenin, which means that this is a 2K resistor, and my Thevenin circuit's done. My Thevenin circuit's done. Without the load, right? This is my Thevenin circuit without the load. All I'm doing when I put the load back is I'm going to check that this V out that we found earlier matches this V out, because then I know I did it right. Okay? So let's go ahead and just do it in SPICE, because I know some people have questions about the SPICE also. So my original circuit is a voltage source, some resistors. I'll call this RL, just so we know that that's our load. It's 1K, this is 6K, and this is 3K. Alright, this is 5 volts, and then this is V out A. I'll just call this VI, I guess. Alright, so V out A should be 1.11, and it is. Okay, so now I'm going to make my Thevenin equivalent circuit, right? My Thevenin equivalent circuit. What I just found was that my Thevenin voltage is 3.33 volts and my Thevenin resistance is 2K. So I'm literally going to copy this circuitry right here. Wow. VI2. Don't label volt. If you're going to do several circuits in the same schematic window, do not label anything the same label, because it will think that you want those connected and it will connect them. It won't draw a wire, but in the net list it will connect them. So if I call this VI, it's going to short these two nodes together. So just so I can show you, let me call this Vout A, and then let me show you what Spice does when I run it. Or here, I'll just do it over here. I just want you to see. Let me just say some I'm just throwing some random numbers because I just want to show this point. So if I run this now, and I say highlight net, it's connecting those. It thinks that these are part of the same net. So what it's literally doing is it's putting a wire between these two nets inside of its own net list. So you don't want to label things the same. What's up?
Would that be beneficial if you had to look at multi-layer circuits?
Yeah, so if you have some crazy circuit and you want to just connect something without drawing wires everywhere, you do use this feature. It's a good feature, but it's a bad feature when you're doing simple circuits because it can cause something like this to happen. Okay? So back on the farm, let me erase this. This is going to be my Thevenin voltage, so I'll call this source, V Thevenin. And what did I calculate, 3.33? Okay, and now my Thevenin resistance, so I'll call this R Thevenin. That was 2K. And now what I'm going to do is I'm going to connect my load. So I'll copy and paste my load. Don't keep it Vout A, because that's bad. Notice that Spice renamed this resistor RL1 because it doesn't want you to call those the same thing. So we'll call this RL Thevenin. How about that? And what I should see is that my V out Thevenin should be equal to my V out A when I run this. So you see V out Thevenin is 1.11, V out A is 1.11. So that means that I did the Thevenin voltage correct, right? Any questions about the Thevenin before I do the Norton? Anything here bother anybody? It all makes sense? So all these circuits that I have down here, these are being used to find the Thevenin voltage and the Thevenin resistance, and then this little thing right here, that's my Thevenin equivalent circuit. I know some people were thinking that this was my Thevenin equivalent or this is my Thevenin. No, these are just tools that we're using to find what we need for the Thevenin equivalent. That's clear? All right, so now I'm going to do the Norton equivalent. Move this down a little bit. All right, so Norton, I'm going to draw the original circuit again. Okay, well, first of all, what we're trying to do is we're trying to find my Norton current, and I already know my Norton resistance because my Norton resistance is equal to my Thevenin, so this is just going to be 2K. And then I'm going to, this is my I Norton, so that's what I'm trying to find here. Okay? So everyone understands I don't have to do this process again because R Norton is equal to R Thevenin, so it's just 2K. It's the exact same process. Okay? So if I do my current, what is it? Oh, sorry. This is where people are getting confused. I'm drawing my original circuit again. 3K, 6K, ground, no load, right? I still have my load removed. But now I'm going to draw a wire between the two load terminals, and I'm going to measure the current that flows through that wire. That is my Norton current. Whatever this current is that flows through that wire, that's my Norton current. That's what I'm going to put right here in my equivalent circuit. And this is 5 volts, right? So this is 5 volts, right? And now, notice that the 6K, both sides of it are connected to ground. This is just a wire. So this is all ground down here, and this is all ground up here. Everybody see that? So the 6K, if I were to do I through the 6K, it's equal to V over R, right? Well, V is the difference in voltage across the 6K. There's no difference there. So that's 0. over 6K, which means that 0 current flows through the 6K. Okay? So when I see this KCL, I know that this is 0 volts because that's shorted to ground. So I have a current flowing here that's 5 volts over 3K, and all of that current flows through my load terminals. None of it flows through the 6K because my KCL tells me 0 flows there, so the rest has to flow here. Yes.
I don't understand why 0 volts flow there, because I think it was-
0 volts.
Yeah, 0 volts.
0 volts. So current is amps.
Oh, sorry.
So 0 amps flows.
Is there any voltage flowing there? Is that?
So voltage doesn't flow, current flows. So just so you keep the terminology straight. I'm not trying to embarrass you. I just want you to make sure you use the right terminology.
So there's no current flowing there?
There's no current flowing through the 6K. And the reason there's no current flowing through the 6K is because the voltage on both sides is the same. So current wants to take the path of least resistance. There's no resistance in this path at all. So all of the current wants to flow through here. That's one way that you can think about it. Another way that you can think about it is mathematically, I is equal to V over R. V is 0. So then I has to be 0. The current flowing through the 6K has to be 0. And if I do KCL, right, I know that if I have a little junction like this and I say that this is my total current, this is my I1 and this is my I2. If I1 is 0, then I2 and I total are equal, right? So all of the current that's flowing through this 3K has to flow through this path. It can't go through this path. Does that make sense?
Yeah.
So 5 volts over 3K, what is that? 1.67 milliamps, something like that? Is that right? So that current right there is the current that flows here, so that's 1.667 milliamps, and that's my Norton current. So that's what I put right here. And then now, let's go back over to Spice. I found my Norton current. I can come over here. So I've got my Thevenin equivalent. Here, let's label them. Make sure you put comment if you're going to label things in Spice, because if not, it tries to take it as a directive and then it gets confused. So this is my Thevenin, and then let's make a copy of this, and we'll call it our Norton. And what Norton consists of, right, is a current source and a resistor. And this is my Norton resistance, which is going to be 2K, the same as my Thevenin. And I just calculated this to be 1.667 milliamps. So this right here, before I connect anything else, this is my Norton equivalent circuit. But I can connect the load, right, to make sure that I did it right. Okay, so just to clarify, this is my Norton equivalent, and then without this here, that is my Thevenin equivalent, but I connect the load to check if I did it right. So again, I'm going to copy this over here. That looks horrible. So let's call this R Norton, R load Norton instead of Thevenin, and let's call this V out Norton. And that V out Norton now should match my other two. They should all be 1.11 volts, and if that's the case, then that means I did everything right. So V out Norton's 1.11, V out Thevenin's 1.11, V out A is 1.11. Everybody see that? So that means that I did my Thevenin equivalent and my Norton equivalents right. Yes?
So I saw somewhere that you can find the Norton current by dividing the Thevenin voltage by the Thevenin resistance. Does that always work?
Yeah, so that's something I was going to talk about today. I'm going to talk about that a little later, so just hold off on that. After I solve these two, I'll solve the other one real quick if people want to see it, and then I'll talk about that. It's called source transformation. I don't know if you saw that. So source transformation is something that I'm going to talk about today because it's very closely related to Thevenin and Norton. Because basically, like you said, right, you can take this voltage source and this resistance, and that V over that R gives you the Norton current. And if you find the Norton current and the Thevenin voltage, you can do V over I to get the Thevenin resistance. You can use them because Right, it would only make sense that if this is an equivalent circuit for this, and this is an equivalent circuit for this, then these are equivalent circuits. They're equivalent. So if I do this V over this R, I get this I. And if I do this, V over this I, then I get this R. It works. It works. That's called source transformation, but I'm going to talk about it later. Any questions about this problem? Do you still want to see me work the second one with the current source? All right. Let's do it. So the next one is homework. All right, so it's homework 7 2B. I'll do the exact same format. Actually, you know what? I'll switch up the color for the original circuit. So this time it's a current source, 5K. That's my load. That's a 2K. Oh, sorry, yeah, I'm still drawing, sorry. Almost done. And 1K. And this is called V out B. All right. So we're back here. Let's split this up again. Okay, so I need to find V out B first. Again, no Thevenin Norton here, just finding V out B as if this was a normal circuit, right? So the first thing I would do is I would put the 2K and the 1K in parallel, and then I can find V out B very easily using Ohm's law. So 3 milliamps, 5K, and then those two in parallel, 2K, 1K, I think it gives me 0.667K. Is that right? And this is still V out B, and it's equal to, basically 3 milliamps is flowing down through this 0.67K, right? So I can find my voltage drop across the resistor. This is 0 volts, so my V out B is whatever 3 milliamps times that is, 2 volts, because it's just 2/3, right? So V out B, that's my original V out B, that's 2 volts. Okay. And let me go ahead and throw that in Spice. So let's copy this circuit. Call this V out B. And then this is a current source instead. What is it, 3 milliamps? And then this is 5K. And then this is 2K, and that's my load, so let's call it RLB. I guess I didn't call this RLA, I just call it RL. And then this is just some random resistor. What is that? R2, R3, R4. And that's a 1K resistor, that's V out B. Call this VIB, I guess. Alright, and we don't need another .op. V out B should be what we say, 2 volts. Alright, so that's right. So now let's go back over here and do some hand calc. So first I'm going to find the Thevenin again. And then I'll find the Norton. So first thing I'm going to do is I'm going to find my Thevenin. My Thevenin looks like this, where this is R Thevenin, this is V Thevenin. And I need to draw the original circuit without the load, right? Without the load. So my original circuit is a current source. It is a 5K, no load, and then a 1K. And then I've got ground. And then this is 3 milliamps, okay. So, again, I need to find the voltage between the load terminals, and that is going to give me my Thevenin voltage, okay? So in this case, I know that I have 3 milliamps flowing through this whole loop, right? It's just one single loop. So what's flowing through this resistor is 3 milliamps. And so then I know that the drop across that resistor is 3 milliamps times 1K, which is just 3 volts, right? Which makes this voltage right here just 3 volts. And if that's 3 volts, and then I know that I'm down here, that's ground, then the difference between those two is 3 volts, and that's my Thevenin voltage, right? So V Thevenin is 3 volts. Any questions with that? Okay. So now I need to find my R Thevenin. And what I do when I do R Thevenin is I short out batteries. I open up current sources. So I know that that's a current source. So I'm going to open that up. Still have no load. And then I have a 1K. This is 5K. And what I'm doing is I'm sending a current in here, and I need to see what resistance does it have to go through to get to the other node, right? Well, it doesn't have to go through the 5K because there's no path for it to flow back to the other node. It only has to go through the 1K. So in this case, my R Thevenin is just 1K. Any questions? I know that can be confusing. A lot of people are probably wondering right now, why in the world does it not flow through the 5K? And the reason is that it has nowhere to flow. If you try to put a current through here, it can't go anywhere. So electrons just will not flow through that 5K. If there's not a complete circuit, electrons won't flow. There's a loop here. It will flow back down to this ground, but over here it will not flow because it can't get to the ground. Does that make sense? Yeah.
Can I attempt to explain why it doesn't flow through the 5K resistor?
Yeah.
It is because there is an open circuit in the middle. So there is no current flow.
Right. This is open, so it's basically like if you were to try and get some. It's basically like if you just cut this wire right now, like my whole computer would shut off. No current can flow through the gap in the air. This is like a gap, right? Okay. So that's it. That's my Thevenin equivalent. I've got a 3 volt with a 1K. So if I come back over to Spice, let's do another Thevenin, and we'll call it V Thevenin B, I guess. And what did I say? 3 volts, 3 volts, and my R Thevenin B is 1K, and then my load, right? So to clarify, this is my Thevenin equivalent circuit. That's the equivalent circuit, and then I can connect the load to check if the output is the same. So my load in this case is a 2K resistor. So I take my load and I plop it right here, and then this will be my V out Thevenin B, and that should match V out B. Okay, so let's run it. V out Thevenin B is 2, V out B is 2, so they match. So that means that my Thevenin circuit's correct. Good with everybody? Yes.
So when you're taking that Thevenin, do you have a current source? You're going to short it? Or what do you call that?
When I'm trying to, what am I trying to find?
When you're trying to find the resistor Thevenin.
So when you have current sources, you open them. And when you have voltage sources, you short them. And the reason you do that is because when you're trying to get rid of a current source, you want to simulate no current flowing. And to simulate no current flowing, you have to open that node. Because if you don't, you will get current flowing. So you open it. And when you want to simulate, when you want to get rid of a voltage source, you want to simulate no voltage across that node. And if you want no voltage, you put a wire there because no voltage drops across a wire. Does that make sense? All right. All right, any other questions? Otherwise, I'm going to do the Norton. All right, Norton. So now, Norton. I'm going to draw my original circuit without the load, and I'm going to short the load terminals together and measure the current there, exactly like we did last time. This is my original circuit. That's a 1K, that's a 5K, that's a 3 milliamps. Everyone remembers that R Norton is just whatever R Thevenin was, so it's 1K, right? So for my Norton, I already know that my equivalent, or my Norton resistance is 1K, right? I already know that, so I don't have to solve for that. All I have to find is my I Norton, and my I Norton is, when I put a wire here, whatever current flows through that node. Okay? So now, if we examine the circuit, again, this is ground, right? This is all ground down here. Well, I just shorted this to ground. So you note again, this 1K resistor doesn't have any current flowing through it because both sides of it are at ground. 0 volts here, 0 volts there, which means all of the current will flow in this path. None of it will flow through the 1K, which means, and I already know it's 3 milliamps. So there you go. My I Norton is just 3 milliamps. Questions? Yes.
Why did you add a ground up there?
It's ground. It's physically shorted to ground. This is all one node now. All of this, all of this, all of this is all connected to ground. So I just draw another ground there to show you they're both ground. But that is all one giant node. It's all ground.
Is there a different simple method to solve this?
Is there a different simpler method?
Yeah, simple.
No. No, there's not.
You could do a source exchange.
I mean, there's different ways to solve problems, yeah, but there's not a different way to find a Norton equivalent. This is exactly how you find a Norton equivalent, right? This problem can be solved a whole lot of different ways, but the purpose of Thevenin and Norton is not to solve the problem, it's to test different loads. So, what's up?
So if you have a circuit with a current source and you're trying to find the Norton equivalence, will the Norton current always be equal to the original current source in the system?
Not necessarily.
Okay.
Because this is a simple circuit, it worked out that way.
Oh, okay.
But say I have other branches of this circuit,
Right.
and there's other things going on, other power sources. So like on your next homework, the one that I specifically told everyone not to put off, it's due in a week, don't wait till Tuesday. You have to Thevenize and Nortonize these circuits. There's two sources. So it will not work, it will likely not work out that way, right? If I take away this 2K and I short circuit across here,
Right.
I'm going to get 500 milliamps, but I'm also getting contributions from this other side.
Right, and then also wouldn't just be equivalent to 0 because that 2 volts is there?
Exactly.
Okay.
So you're still going to get current. So this, let's say we short this.
Right.
This will be 0, right?
Uh-huh.
This will be -2 then.
Right.
And this will be 0. So you have current flowing through this 1K, and that will pour into that
Right.
node, right?
Okay, that makes sense.
Yeah. Okay, yeah. So I'll come back to this later, but as far as this homework, so any other questions? I'm going to build it in Spice next. I found I Norton. Does anybody have any questions about this, what I just did? All right, so let me build it in Spice. So I know it's let me just copy this. All right, so this is going to be 3 milliamps. This is my, I should call this I Norton A, and this is I Norton B. Whoops. My Norton resistance for B was, what is it, 1K? Yeah, 1K. The same as the Thevenin, right? The same as this. And then my load, so again, I just want to clarify this. This right here is my Norton equivalent. And now I'm going to connect my load, same load as the Thevenin, and I'm going to measure to see if that's the same output. And then if it is, then I did this right. So let's run it. So V out Norton B should be equal to V out Thevenin B should be equal to V out B. 2 volts, 2 volts, 2 volts, right? So that right there is exactly what I would want to see on this homework. This is the 3 for part A, this is the 3 for part B. These are the hand calculations that you should have. Yes?
So just to clarify, can you go back to the other one?
The Spice?
Yeah. So when you take off the load and you short it, that's when you want the Norton equivalent, that's the Norton equivalent you're asking.
So when I ask for the Norton equivalent circuit, If I get rid of the load, that is my Norton equivalent. Not with a short. You're not going to short that. It's basically a current source with a resistor in parallel, and now you're waiting to connect something.
Oh.
That is my Norton equivalent. So you don't have to have these terminals here either, right? If I nuke this and this, that right there is my Norton equivalent circuit. But I keep them there because I'm basically waiting to connect the load. But this circuit and the circuit where all of that stuff is gone, right? Sorry. This circuit is the same exact thing as that circuit. I've just drawn those wires out, right? Okay. Yes.
In Spice, is there an easier way to measure current flowing through a wire for the sake of verifying our I-Nortons?
So yeah, if you wanted to,
Zero ohm resistor, I guess.
don't do a 0 ohm resistor.
Okay.
Do a 0 volt voltage source. So if let's say I wanted to, let me make a copy of this. Find my Norton current. You found your Norton current and you want to make sure you did it right.
Yeah.
Basically, delete the load and put a voltage source there, right where you want to measure the current, and make it 0 volts. And whatever direction you want to measure it in, so I want to measure it going down, make sure that that's the direction of the plus to minus. So it will measure the current now flowing down through this node. So what did we measure it to be? 3 milliamps?
Yeah.
So my I through V2 should be 3 milliamps. I through V2 is 6 milliamps. What? What did I do wrong?
Is there a different V2?
Is there another V2?
There's another V2.
I don't think there is.
Okay.
Oh, it's because I called this V out B. See? See? V out example.
Oh, wait, you also have the other one is
Yeah, it's not
VIB.
VIB connected.
You have VIB. Is there anything else?
See guys? Alright, so I through V2 is 3 milliamps. So there you go. So that right there is how you would measure your short circuit current. Or through any wire that you want, you can do that. Okay?
Why not use the 0 ohm resistor?
It causes problems in Spice, and it'll just short it, and it'll call this ground, and then you won't be able to measure the resistance.
Okay.
So if I go here, just so you can see it, if I put a 0 ohm and I run this, it's just going to say now that that node is ground. It's not going to, it says this is ground. Do you see that? Right here? This is ground. This is ground. And it won't let me, if I go back to the net list, it won't even show a current through R7. R7 won't even be listed here because it just takes it as a short. So if you put a battery, it doesn't do that. If you put a resistor, it does.
Okay.
I'm assuming it would be the same as a wire. If you put just a wire in.
If you put just a wire, yeah, it'll say this is ground, and then it won't. Obviously, nothing's going to pop up in the net list because that's just a wire. So if you really want to measure the current through something, put a voltage source there. 0 volt voltage source. All right. Any questions about that? What I just did, I'm going to go through source transformation now. It's really simple. I think you guys will like it. Also, just might as well announce now, I'm not going to give a quiz today. So don't worry about the quiz. I'm going to use today to make sure this is clear before I send you guys away for a week. When's the exam? It's just a midterm. So I have a midterm and a final. It is on March 9th.
Oh, I didn't realize we had next Monday.
Yeah, so there's nothing Monday, nothing's due. That's why the homework Wednesday is a little bit longer. It's worth more points. I don't think it's unreasonable, like I said. I want to talk about that before you guys leave, but let's get into source transformation so I make sure I have time to cover it. And so I'll talk about source transformation by itself first, and then I'll talk about it in terms of Thevenin and Norton. So basically, you're going to see this is very heavily related to Thevenin and Norton. That's why I wanted to teach Thevenin and Norton first, because I thought that this would be really easy for you if I did that first. And I think that it should be very easy. So basically source transformation, right? If I have a voltage source and a resistor, this is just going to feel like dumbed down Thevenin and Norton, so just bear with me. If I have a voltage source and a resistor, like so, a voltage source with a series resistor, there exists an equivalent current source with a parallel resistor. Right? You might be like, well, no crap, that's exactly what we just did, right? But this is not in that context. This is in the context of actually solving problems. Like if I have a circuit where I have a current source and a parallel resistor, I can replace it with a voltage source and a series resistor, and I will get the exact same result for that circuit. So let's call this R, this is going to be V, this is going to be the same R, and this is going to be I. Okay? So that's basically source transformation right there. Interchangeable. If I have a current source, parallel resistor, I can transform it into a voltage source with a series resistor and vice versa, and it makes solving problems a lot easier. So let's say I had a circuit that had a current source of 3 milliamps and a parallel 1K, and then I have a 2K resistor out here. Right? I can take this little chunk of circuitry right here. If I don't, let's say I just hate current dividers. Current dividers drive me absolutely nuts. And I want to use a voltage divider. Well, you can. You can transform this into a voltage source with a resistor, and then you just have a voltage divider. Right? And it's going to give me the exact same V out. Again. And how do I do that? I'm just going to use Ohm's law. So, right, I'm going to write the three versions of Ohm's law here, basically. V equals IR, I equals V over R, and R equals V over I. Right? That's Ohm's law. So that's used for source transformation. So if I have this I and this R, and I want to find the voltage, I do I times R. That's it. So 3 milliamps times 1K gives me 3 volts. So my equivalent circuitry here is going to be a 3 volt in series with a 1K. That makes sense? And then I plug the 2K right back in. And this voltage, V out, will be equal to that voltage. So I just took this 3 milliamps and this 1K and transformed it into 3 volts in series with 1K. Okay? And I will get the same output. So this is used if you see a circuit where you're like, man, this looks like a pain in the ass to do with a current source and a parallel resistor. Let me just transform it into a voltage source and a series resistor. Or it can work the other way. If you don't like this and you do like this for some weird reason, you could go the other way. It just depends. I think voltage sources are easier. Does anybody think current dividers are easier than voltage dividers? All right, cool.
No one likes parallel circuits in general.
Yeah, I mean, you learn to get used to them, but I think voltage dividers are just so easy to see and just makes sense.
I like capacitors in parallel.
Capacitors in parallel? Yeah, that's fun. You just add them.
They're funny.
All right, so just to prove this to you, let's go throw it in Spice. Let me just make a new schematic. So originally I had a current source, I had a 1K, and I had a 2K. Additionally, here, you know what? I'm not going to get into that yet. We'll talk about it later. Yeah, I want to wait. I don't want to. I'm in the middle of this, but no, I'm just. So to clarify, right? Let me copy this. I am taking this piece of the circuit and I am replacing it with a voltage source that I just found to be 3 volts. And a 1K resistor in series. $3 volts.
So if it went the other way, you would change it
Yes.
Well, what if you have voltage in parallel?
Then you can't do a source transformation.
Okay.
Yeah. So it works for a voltage source with a series resistor or a current source with a parallel resistor.
It kind of follows the two laws.
Yeah. Yeah, exactly. What's up?
So it would work if you have a voltage and then the two parallel resistors and make it to
One series resistor?
Series resistor.
Yeah, that works. Yeah.
So you just do the resistor equivalent?
Yeah, so if you have like a voltage source and then that, so let's just go back over here. So say I had, what it sounds like you're asking about is if I were to have like a voltage source and then like a resistor and another resistor and then some other circuitry. I could take these, combine them in, parallel. That would give me something that looks like this, and then I could do source transformation if I wanted to, with this being the equivalent of R1 and R2, right? You wouldn't, but you could. Yeah, you could. All right, so these are so this is going to be V out 1. We'll call this V out 2. So those should be equal. If they're not equal, then I'm fired. Oh, please be equal. Nice. All right. So that worked. Guys. All right. So basically, you realize that you can do this. I can transform this current source parallel with this resistor into this voltage source series with that same resistor, and vice versa, if it makes solving the problem easier. Okay? You don't have to do it. You could have just solved for V out like this, but if you just prefer the voltage divider and you don't even want to deal with this, you can do that. So now how does this tie into Thevenin and Norton? Well, if I have the Thevenin circuit, I can just do source transformation, and that gives me the Norton circuit, and vice versa, right? So if I come back over here, right, this is a voltage source with a series resistor, this is a current source with a parallel resistor. So if I take this V over this R, that gives me my Norton current, and then I have the Norton circuit already. I don't even have to do the short circuit stuff, right? So the reason why this is important, right? The reason this is important is because there's three things you have to find here. You have to find the Thevenin voltage, you have to find the Norton current, and you have to find the resistance, the equivalent for the Thevenin and the Norton. How many people dislike finding the resistance the most? That's it? You guys like the resistance? Which one's the worst, the current?
The Thevenin voltage for me is the worst.
The Thevenin voltage is the worst?
I think the current is fun because you just put a wire and it usually makes something go away.
Well, personally, I hated finding the resistance. So I would find the voltage and I'd find the current, I do V over R, and now I have the resistance. Okay? So whichever one you dislike finding, you don't have to find it. You can just find two of them. Whichever one you hate the most. So if you just hate the voltage for whatever reason, you can do I times R, and that gives you the voltage. So you don't even have to do it. So that's why this is important. So on the next homework, right? On the next homework, let's go back to homework 8. So for these, you can, by all means, you can find the Thevenin voltage and you can find the Thevenin resistance, and then you don't have to find the short circuit current or whatever to find the Norton current. You can just do V over R, and that will give you it because of this property of source transformation here. So any given one of these, if you have I and R, you can find V. If you have V and R, you can find I. If you have V and I, you can find R. That works for any circuit that looks like this, and it also works for any Thevenin and Norton equivalents that you already found. Does anybody have any questions about source transformation? Because I went through it pretty quick, but I figure it's probably self-explanatory after we already did Thevenin and Norton. Does anyone have any questions? All right, so now I want to talk about the next homework. Maybe I'll even solve one since we have some time.
Yeah.
So let me close Spice. All right, so basically this homework is a bunch of Thevenin and Norton with some more complicated circuits. They're not incredibly complicated, but they are more complicated. So I'll solve one of these, whichever you guys like. And then down here, these are some 3-loop circuits. You guys haven't seen this yet. And I'm asking you to solve for the voltages and the currents in these circuits using both mesh and superposition. And what I mean by that is I want you to solve it using mesh and get your answers, and then I want you to solve it using superposition and get your answers and clarify that they match. Okay? The mesh for these are very easy. The mesh is very easy. Instead of 2 equations, you have 3 equations, and I was nice enough to give you a current source. So it's just 2 equations, really. Okay? The superposition is very difficult. I solved them last night, and it took me a while. So if it takes me a while, it's going to take you a while. I hope it doesn't, but I think that it will, just because you're just getting a weird look at things, right? It looks overwhelming, and it's going to take some time. So I just don't want anyone to put this off until Tuesday and then just be drowning, because this is a 20-point assignment. It's 10 points for the top, it's 10 points for the bottom. So this is a big homework. This could really boost your grade if you do well. So start it early, work on a little bit at a time. If you have questions, ask. I'll be here throughout the rest of this week and next week. For if someone needs to come to my office, just email me. I may or may not be here. But for now, I'm not going to solve these because I don't think I need to. I could solve a 3-loop circuit, but I don't think it's worth it. It's just the same thing. You make your 3 equations and then you solve the algebra. If you know how to do a loop equation for any of these using KVL, it's the exact same thing. It's just going to be the algebra that's going to be annoying. But again, I gave you current sources, so there should only be 2 equations, 2 unknowns, really. What's up?
So you can use superposition to find out all the voltages?
Yes, good question. So originally I was like, find VA2 using superposition.
Yeah.
Well, if I find, so say I'm going to do superposition for this problem. The first thing I'm going to do is I'm going to get rid of this current source. I'm going to open it, and I'm going to find VA2, I'm going to find VA1, I'm going to find VA3. And then I'm going to get rid of the voltage source, and I'm going to do the same thing. They will add to be the same voltages.
Okay.
So if I get VA1 with the current source removed, and then I get VA1 with the voltage source removed, and I add those, that gives me VA1. Same thing for VA2, same thing for VA3. Same thing for any voltage you want. Okay? What's up?
And just making sure you short the battery and open up the current source?
Exactly. Yeah, so if I were going to find, all my voltages here, I'm going to get rid of this current source, which gets rid of this entire branch, because that's an open, and now I'm just left with 4 resistors and my voltage source, right? And then you have basically 2 KVL loops, and you can find the currents and find the voltages. Basically, these problems are going to test everything that we've done so far. They're going to test your ability to do KVL, they're going to test your ability to do KCL, mesh, superposition, combining resistors in parallel and series. So these are like all-encompassing problems. If you guys can solve these, like reasonably solve them, you will have no problem on the midterm. Like you will not have a problem on the midterm. So definitely try and do these problems to the best of your ability. If you get stuck, obviously ask. Use these problems over and over again and different variations of them to study for the midterm, because if you can do these problems, you can do anything. Like these problems have everything in them other than Thevenin and Norton. But that's what problem 1 is for. What's up?
For number 2 real quick. So just to understand, when you open up the current source, like those dots represent what's affected by that current?
What dots?
Like the dots of the dot of the icon.
These?
So the wires are connecting.
All that is it's like a junction for multiple wires connecting. So anywhere that like 2 wires are orthogonal to each other, you basically have this junction. It's telling us that those wires are connected. So a lot of people, what they did on this previous homework, was they like drew a wire like this, and they drew a wire like this. Those wires are not connected. They're not connected. If you don't see that dot, then that means that they're not connected. So a lot of people made that mistake. If you don't see a dot there, that means that they are not connected to each other. So don't do this when you have wires crossing. Make sure that you actually, draw to the connection and then past it.
And just one more question. Why is the 5K effective at the current date?
This 5K?
Yeah.
Because it's still connected to this loop. The only reason why the 5K, so if there was a resistor down here, and I open up the current source, there will be no current flowing through that resistor, because it won't be a part of any loop. But this one is still a part of this loop, so it's still, right? Okay. I have like 15 more minutes. Somebody pick one of these for me to solve. Whoa, I did A, B, C, B.
A, B, C, B.
Let's do B. Let's do B.
B.
That's annoying.
Everyone agrees on B, right?
I'll start with the first one. The first B. I shouldn't have even pointed that out. No one would have noticed. All right, so let's do B. Let's do B, the first B, the original B. Maybe. We'll see. How many of you guys would say this is your hardest class?
No.
Yeah? All right, well, that's good. That makes me feel better. I thought everyone was going to be like, this is the worst class ever. It's the hardest class I've ever taken. Yeah, CPU200 is hard. I think that's a hard class. Yeah, that class is... It's hard and it's unnecessary.
I think it was easy because I took econ in my last year of high school and I took that.
Oh. If you have some econ, it might, like background, it might not be that bad, but if you don't. Alright, so we've got the load is this 2K, and we want to find our Thevenin and Norton equivalents. Oh my god, no. Why? Why? Oh, it's an hour and 2 minutes. Okay. Whew. I thought that was a minute and 2 seconds and it was frozen. I was gonna lose it, guys. I was gonna lose it. It's like, why? What happened? Dude, I don't get it. I have had so many technical difficulties this semester. I mean, it's the only time I've ever taught, but this semester has been the worst semester ever. It's also been the best and the only.
I think it's because you became a teacher. Teachers have inherent negative technology words.
Yeah, that's true. I'm literally a master's in EE and I don't know how to work a freaking document camera. Alright, so what you're going to do first is you're going to find that original V. I'll call it V out. It's VB in this case, but that original voltage needs to be found nonetheless. So what you could do is you could do a quick mesh. I'm going to do none of the above and throw it in Spice because I don't want to try and take up a bunch of space on my paper. I don't think anybody has problem finding this V out, do you? Like, you could just, oh, this is I1, do a KVL. I'm just going to throw it in Spice because I don't want to take any time. We're running low on time. Okay, that looks like that, and then this is 2. Alright, that goes there, that goes there, this is ground. Ugh. 5K, 2K, 1K, V out. Alright, run 1.667 volts. Alright, so that's what I'm going for.
For our homework, do you think the grader will care if we don't show our work for finding our original VOs?
Yeah, I want you to find them.
Okay.
For practice. Definitely do. Definitely do. What?
Do show the work.
Do show the work.
Okay.
Definitely find them by hand because it's good practice. I just am running low on time, so I don't want to waste time doing something you all know how to do already. So Thevenin. So what am I going to do first? I'm going to get rid of the load resistor the 2K, and I'm going to find the voltage between those two points, right? So my Thevenin looks like this, right? This is my R Thevenin, this is my V Thevenin, and I am going to go ahead and 5K, open, 2 volts, and then a 1K. Okay, so I'm trying to find the voltage between these 2 points, and that's going to be my V Thevenin. Yes?
The question says to do it with the load connected, you're supposed to take it out.
Did I really say that? If I said that, it was probably a mistake. No.
Load resistor is.
Find the Thevenin Norton equivalence for the given circuits when the load resistor is removed.
Oh, okay.
And then it says verify that your equivalents are correct by simulating the original, the Thevenin, and the Norton when the load resistor is connected. All right. So this is one loop. Everyone agree? One single loop here. So 0.5 milliamps flows through this. So 0.5 milliamps flows there. It flows here. If it flows here, 0.5 milliamps times 1K, this gives me 0.5 volts, right? And now this goes up by 2 volts. So that means that this is 2.5 volts. And that's my V Thevenin, right? That's the difference of voltage between these because this is 0 volts. So V Thevenin, 2.5 volts. Are these starting to feel easier? That makes more sense? Okay, so now I want to find R Thevenin. And what I'm going to do is I'm going to open the current source. That's still an open. That's still ground. I'm going to short the battery. And so, yeah, all of them go away when you do, this is not superposition. It's just when you get rid of the sources, you do the same thing that you do when you get rid of them in superposition. But you're going to get rid of all of them, and then you're going to measure the resistance. If I send a current in here, how much resistance does it have to go through to get to the other side? 1K, because it doesn't travel through the 5K because it can't. It has nowhere to go, right? So R Thevenin is 1K. So that's going to be my Thevenin equivalent, right? This is going to be 2.5 volts. This is going to be 1K. And then what I would connect out here, my load, right? That is, what was it, 2K? So I put 2K here, right? And so you can already, let me just make sure that that's right. 2.5 times 2 over 3. Yep. So if I take this voltage divider, right, I have a 2.5 volt, and then I have a 2K and a 1K, right? The 2K is my load. I put it back in. I'm trying to calculate this V out to see if it matches this V out. If I do that voltage divider, I would do 2.5 volts times 2K over 3K, and that gives me 1.667 volts, which I can confirm that that was correct, right? I'm not going to go and do it in Spice because I'm running out of time. What's up?
So, would there ever be a case where the load resistance, there's like more than one load resistance, there's like two, when you're using Thevenin and Norton, or is it specifically with one?
Well, the thing is, like I said, we just use resistors to model a load.
Right.
You're never going to actually have a load that's a resistor. It's probably going to be a light bulb or something you're trying to power. So when we say that this is our load resistor, it's literally just this is what we're using to model our load. So that you're never going to have like 2 load resistors. It would just be 1.
Right.
Or what's up?
Sorry, no, I was just going to say things that we're trying to power have resistance.
Right.
Using a load resistor is just to say it's fine.
It's just a model because basically what you have is you're going to say you have like a voltage say you have a battery and you just want to plug it into an LED and power up that LED. That LED is going to start immediately pulling current. That LED is my load. And say it pulls 20 milliamps. So let's say it pulls 20 milliamps. I want to put a resistor on the output of that battery that's going to pull 20 milliamps so that I can model that load.
Right.
So I would have to do Ohm's law, whatever let's say it's a 9-volt battery, 9 volts over what resistance gives me 20 milliamps. That resistance is what I would use to model that load. Does that make sense?
Yeah.
Okay. All right, any questions about this Thevenin? Okay, so I'm going to do Norton.
Do we still need to do them all out, or can we use source transformation to find the third?
Oh, that's a great idea. Let's just do source transformation. Do you want me to do it out? Do you want me to do it?
I'm saying for the whole
You can
thing.
do source transformation.
Okay, that's awesome.
Yeah.
You can do however you want.
Yeah, if you want to do source transformation, that's fine. I'll do the full method just so that we can see it. So now I'm looking for my Norton current, right? And then I'm going to connect my load, right? We already know that the Thevenin resistance is 1K. My load is 2K. So all I need to find is I Norton. And so what I'm going to do to find I Norton is I'm going to draw the original circuit. 0.5 milliamps, 5K. My load is gone. I've got my battery here. So this is that one that I was telling you about, right? This isn't just going to be 0.5 milliamps. It's going to have a contribution from the other source. So I know that this is my circuit. This is where I want to find the current. I want to find the current flowing through here. And I know that this is a 2-volt source. So basically, I know this is 0 volts, right? This is all ground because I just shorted that to ground. Okay? So I know for sure that I have 0.5 milliamps flowing in there, right? From that source. But how much do I have flowing over here? Well, this is 0 volts. This is 0 volts, and this drops by 2. So this goes down to negative 2 volts right here. So that means I have another current flowing in this loop. And that's going to also, pour in there and contribute, right? They both go through that node. Well, what is my resistance out here? 1K? So I've got 0 volts minus negative 2 volts over 1K, which is 2 volts over 1K, or 2 milliamps, right? That plus my 0.5 is the current that's flowing in there because of KCL. So I've got 0.5 milliamps plus 2 milliamps equals my Norton current. So my Norton current is going to be 2.5 milliamps. So this would be 2.5 milliamps. That does not look like a milliamps. And now I'm done. I would have to check that this checks out. Basically, I'm going to have a current divider, and then you can check V out and solve for it. I'm not going to have time to solve the other one, but it's the same process over and over, right? All of these circuits use that exact same process. You go through that process, you're not going to have any problems. This is where the bulk of the time I think is going to come in. So definitely don't put this off, like I said. And that's all I got for today, unless anyone else has another question. Good?
Okay.
Yeah, what's your question?
Mildly related. So when we were doing the Thevenin equivalent for the question that we were just doing, we had the current source that was 0.5 milliamps flowing through the voltage source. And then the resistor passing, we were saying 0.5 milliamps flowed through that resistor. When we, on the left, the Thevenin equivalent.
Oh, over here.
So when we opened our load, we said that we have 0.5 milliamps flowing through the 1K resistor in order to give us the 0.5 voltage on the negative terminal of the battery, correct?
That's right.
Does the battery not contribute any current in this particular situation?
The battery, it does contribute to the current.
Right.
But the thing is, actually, no, it doesn't contribute to the current. It sets the voltages that are in the circuit. But this, since it's only one loop, this current source sets the current.
Okay.
Does that make sense? Like, since it's here, let me stop the video.